to be launched.
All right, welcome back. I'm Sarah Jennings, the executive producer for FDL in the US, and I'm excited to have another SETI Live with our FDL teams. So Frontier Development Lab is an applied artificial intelligence research accelerator. We bring the brightest minds from around the world in space science and exploration domains, and we pair them with machine learning researchers to tackle problems in the areas of heliophysics, astronaut health, lunar exploration, and earth science. This is our 5th year doing FDL with a program that's hosted by the SETI Institute and in partnership with NASA. And this is the first year that we are taking it virtual. We have 8 teams that are working together and going through our 8-week program, and we're currently on week 4, where teams are focusing on calibration. And earlier this week, we had an amazing chat with our Knowledge Discovery Framework team. And today, I'm excited to have the Geoeffectiveness team. So I'm going to go ahead and kick things off with introductions. Panos, can you go ahead and introduce yourself?
Sure. So, yeah, my name is Panos. I'm originally from Greece. I'm doing a PhD on machine learning at the University of Oxford. And I'm currently in Greece. Since everything is remote, I decided to be around the sea.
Great. Thanks, Panos. All right, we'll move over to Vishal.
Hi everyone, I'm Vishal Upendran. I'm a graduate student at Inter-University Center for Astronomy and Astrophysics, IUCA, in Pune, India. I work in the field of solar physics. I use machine learning techniques and statistical techniques to study the sun.
Great, thanks Vishal. And we have Téo.
Hi, I'm Téo Bloch. I'm a PhD student at the University of Reading in UK, and I do my PhD on applying machine learning to space physics.
Great, and Bashi?
Hi, I'm Bashi. I'm currently at University of New Hampshire. I'm a research scientist. I did my PhD from there in space physics, and I'm using magnetohydrodynamic simulation models to study the relation between Sun and Earth magnetosphere.
Great, thank you, Bashi, and thank you all for taking the time to be here today, as I know you guys are deep in the problem. So I want to go ahead and kick things off with asking if you can go ahead and tell us a little bit about the challenge that you're working on. So Bashi, I'll turn it over to you.
So actually the study of the weather is not just limited to changes in atmospheric conditions like winds, clouds, precipitation system, and the constant emission of the solar wind creates another type of weather, which is called space weather. The space weather specifically focuses on the relation between the sun, a magnetosphere, ionosphere, and the Earth's system. Basically, we are affected by the solar wind condition, our power grids, our telecommunication system, and railway system and pipelines could be affected. And this challenge is not new. Like, for example, if such a solar storms happen previously in 1989, that the whole Quebec state went without power for hours. And then there was this historic event, the Carrington event, and which happened in 1859, which there was fire in telegraphs, and there was problem with the communication system. And the National Science Foundation in 2008 estimated if such event happened to us, it would be devastating. It would cost us $2 trillion, is 20 times of the cost of Hurricane Katrina. And so with this challenge, we're going to study the relation between the sun and Earth magnetosphere using the both ground-based and space measurements. So we hope to be able to forecast if something solar storm is coming towards us, like at what location and to what intensity we would be affected.
Thank you, Bashi. Yeah, that's a great overview of both the challenge and why this challenge matters to us. The work that you're doing is obviously really important and relevant to everyone here. So I would like to learn a little bit more about the sort of tools and processes that you guys are using to address this pretty big challenge. So for that, I'm going to go ahead and turn it over to Panos.
Sure. Okay, building on top of what Bas mentioned, so our goal is to forecast, given, let's say, some measurements that we get from satellites, which float between the Earth and the Sun. We want to measure, we get the measurements from that point, and then we want to predict and forecast what's going to be the impact on Earth. So on Earth side, we have already some sensors that measure the magnetic disturbances on Earth. There are around like 250 stations currently spread around the globe that we are using, where we can see, for example, at a specific time, what is the distribution or like the perturbation on the magnetic field on Earth. So our challenge is to get, let's say, a sequence of measurements from the satellite, which is between Earth and Sun, and forecast the sequence on you know, what's going to be a sequence of events that we will probably observe on Earth. So for that, we currently use deep learning. Surprise. So lately there will be like a great advances and great like examples where deep learning has been super successful. For example, autonomous driving, or forecasting generally sequences, or translation like from a language to a language, or even like generating audio samples like text to speech. And specifically mentioned the translation problem and the speech generation, because there are certain similarities to what we are doing. For example, in a translation problem, you have a sequence of words from one domain, a language, and then you want to translate to a new language. So this is a different sequence. So we use similar models and deep learning techniques to that, where essentially we get a sequence of symbols. In our case, our measurements from the satellite, and we're trying to translate to a new language. So this language is essentially the measurements that we receive on Earth. Obviously, this is like, okay, there is a time dimension to it, where in language is a different semantics. So we have, for example, the problem in our case where we don't know what is the cause and effect duration, or like the measurement that we get from the satellite to how long it will take to receive an impact, to measure an impact on Earth. And I guess Vishal or Téo might talk more about the issues there. So, and also I mentioned the audio generation. So lately there was a model produced by DeepMind, which was called WaveNet, and it was actually quite fascinating to see that you could generate sequences of audio that sounded like, like not AI generated. They sounded very natural, and that was very interesting because there are a lot of there's a lot of complexity in the audio, and predicting or figuring out what each sample of let's say even 5 seconds audio would be. That's a very challenging thing. And in our case, also we have a similar complexity in the sense that there is a lot of like underlying physics that we hope to our models to learn how to model, and that's why we get inspired and we follow that kind of work, like NLP, like a translation between languages, and also audio generation.
Great, thank you, Panos. That's some great comparisons that you were able to make there. So my next question is, if you can talk about, you guys are in week 4, you're about halfway through FDL. What are some of the roadblocks or issues that you guys are currently working through? And I'll go ahead and turn it over to Téo for that.
Yeah, so I guess starting from some of the more obvious ones is, on the one hand, we have a big data problem, which means that we're having loads of issues processing large amounts of data and getting it into usable formats. Ironically, we also have a small data problem in that all the major events that we really care about are very rare. And so it means trying to learn anything about how they interact with the Earth through machine learning is a really difficult task. So it's quite funny to have both big and small data problems in this regard. But the other thing, as Panos mentioned, was sort of lag times, where we have a system where the time between cause and effect depends on the type of cause that you have. And then after that, it depends on the location of where you're trying to measure an effect. And these are really like non-trivial links between the two things. So even if you might know all the different causes, how it relates to different places on Earth where you might measure the effects, it's really difficult to gauge. And even coming up with things to look for to judge the effect in and of itself is another problem that we're having, where the good definitions might be more difficult to come by, and it's a lot more specific rather than generalized. So it's hard to get a nice global feel for how these things happen and what kind of effects they have. And that's a big part of what we want to try and get out of our project, is to be able to have a global definition for what sort of activity we can see on Earth.
Great. Thank you, Téo. So I want to take a moment. I see some of the questions are trickling in. Just a reminder, if you're joining us in the audience, we would love for you to ask us questions. So feel free to type those in, and we'll open it up for Q&A in just a few more minutes. Also wanted to welcome some of our viewers that are joining us from all around the world: Scotland, Oklahoma, New York, Quebec, the UK, Michigan, Virginia. Welcome, and thank you guys for joining us. So I'm going to go ahead and keep asking the team some questions here. So Vishal, I would love to know, now that we've heard a little bit more about the challenge, what are you guys hoping to achieve at the end of this program, and what is your desired outcome for this challenge?
Yeah, so there are a couple of things here. First thing is, we have these measurements on Earth. So what are these measurements? These are changes in the magnetic field measured at various locations on Earth. Ideally, what you would want is to predict these magnetic field perturbations, as we call them, much before they even occur. So how long, how much time before would you want to predict these measurements? 2 hours, 4 hours, 10 minutes? So it depends on what kind of data you have. So there is a causal effect between the measurements in space, in situ as we call it. So that's measurement at a given point in space and the Earth. And there is a relation between the measurements you do in remote sensing, or if you take an image of the sun, let's say, a measurement drop the image of the sun and an effect on the Earth, that has a different delay. So ideally, what you would want is to take an image of the sun, or take a sequence of images of the sun, and let this machine learning model tell us at each place on Earth what is the magnetic field perturbation going to be. That's a very difficult problem to solve. So we just break it down into various steps. So you have a simple model, and then keep complicating it till you are able to get a really good output. So the first simple subcomponent of what we are going to do is we have measurements of the solar wind. The solar wind is a stream of particles coming from the sun, and it's measured near this point called L1. It's a point in space near the Earth. There are plasma measurements at this point, and we seek to translate from this point to the Earth. So as Panos was saying, there is a language to language translation. The two languages here are the plasma measurements at this point L1 and the magnetic field perturbation measurements on Earth. So that is the first deliverable we seek to have, a perturbation prediction algorithm. The second deliverable is the generally machine learning models just give you an output, but these models don't tell you how confident they are about their outputs. So given that you get some output, some 5 nanotesla, let's say, but are you sure it's 5 nanotesla, or do you think it's 7 nanotesla, or it's 20? How do you quantify that? There are a lot of statistical methods in the machine learning literature through which you can get these error bars, as they call in scientific terms. And this will tell scientists whether they should trust these measurements or not. And these things are lacking in the geophysics community. And finally, I mean, the holy grail would be to just take measurements from the sun and somehow translate that using a model to L1 point, and then append a model of L1 point to the Earth next. So that's the big goal we have in mind.
Great, thank you, Vishal. And you guys are in a really unique position where if you guys have been following us, had a challenge last year that was also focused on geoeffectiveness. And I just wanted to hear from you guys how you've been able to take what they did last year and learn and build on their work.
I can take this one. So I guess some of the things is learning from their choices of models that they made, and like specific bits of code that were written for last year's challenge are things that we've incorporated into how we're doing our analysis. So in some ways that's streamlined, at least definitely the early stages of getting the data and organizing it and stuff, and made that much faster. And we also have the benefit of being able to talk to people in the team last year if we have questions. So I think on Monday we had a meeting with one of the team members to talk about how they dealt with problems with data gaps, for example. And so we got some good one-on-one time to really have a chat about the problems they faced in the same regard, our thoughts on how to address it, which ones they tried already, and which directions we should maybe go in next. So that's been really helpful for us in like guiding through the kind of more tricky parts where we don't have necessarily the exact experience.
Great, thank you. Yeah, you guys are in an exciting position here. So we do have a few questions that are starting to come in. So one of the questions is from Jim. And Jim is asking, has the Earth ever been hit by a major solar storm of the magnitude that we're describing here today? So Bashi, I'll go ahead and turn it over to you.
Yes, as I mentioned earlier, so there were so the biggest event that we have, it was in 1859. And so the advantage that we had that time, we were not dependent on technologies much. We didn't have like power grids. So the only, the telegraph system were in fire. In the modern life that we are in, there was in 1989, there was storm that hit Quebec, and then the whole state were out of power. So when we say like you're going to be out of power, it's just not like the snowstorm that one street or one small area. So the whole state might go out of power, and to rebuild those power grids, it's really time consuming and it's really expensive. And another storm that I remember that was fun is called Halloween storm in 2003. And I remember my friend was telling me when they were going to trick or treating, so they were seeing all these shades in the sky. That's actually were aurora that they were seeing. But but these are the ones that I'm just like giving. There was like big consequences, but there are more than that. They're happening all the time, and so their scale changes. And there was another one that actually did not hit us. It went away from the sun. So if you imagine sun is rotating, and if like they have this coronal mass ejection that comes towards us, and like because these coronal mass ejections were going away from the sun, they didn't hit us. And if that would have hit us, that they estimated that would be around $2 trillion just for us.
Thanks, Bashi. I know that ever since I joined FDL, I definitely pay more attention to space weather than I have ever before. So I'm going to go ahead and follow up with Téo on a question about why is machine learning potentially particularly well suited to help solve this problem?
So with the problem that we've got, what we expect is that we have the solar wind coming towards Earth. It hits Earth's magnetosphere, and the magnetosphere, the effect of that collision is translated down to measurements that we can make on the Earth. And since there are physical laws describing this, there is some way we can map to what is hitting the magnetosphere to what we measure on the ground. But what those physical laws exactly are and how they all like relate into each other is really tricky to piece together from the data we have. The benefit of using machine learning is that it's a really efficient way to use a very large amount of data, wherein the machine learning model attempts to learn what that mapping is from the solar wind to what we measure on the ground. So we're trying to make a model which can do that mapping specifically, rather than being limited maybe by potentially bad data or having to spend a lot of time with the theoretical approach to it. We can actually use machine learning to let the data tell us what this mapping is. And given that we do have so much data that is in other ways quite difficult to use without machine learning, this is the perfect opportunity to really make use of everything that we've got to try and understand more about how that interaction works.
Great, thank you. Yeah, I'm excited to see what you guys come up with by the end of the 8 weeks and beyond. So I believe the next two questions I'm going to go ahead and turn over to Vishal. So we have the first question is from Edward, which is, why is the sun's photosphere hotter than the surface? And then the other one is tied to that, I believe, Vishal, but I'll let you go ahead and respond to that one first.
Yeah, so the question actually is not really correct, because the sun's surface is the photosphere. It's not, they're not two different things. What is hot is the atmosphere called corona. So as you go away from the surface of the sun, the temperature first drops and then it starts rising. I mean, it's logical that if you consider a heat source, if you consider a campfire, and you start going away from it, the things get colder. But from the sun, if you start going away from the sun, first it starts getting colder, and then it starts getting really hot. So it's like 1,000,000 degree Kelvin in the atmosphere in this region called corona. So the problem that the question asks is called the coronal heating problem. And yeah, I'll let you ask the second question so I can just answer them together.
Great. Yeah. So the second question that you touched on a little bit is related. So question on the new close-up images of the new phenomena called campfire, and your thoughts on that. That's from Joshua.
Yeah, that's a very nice question. I like it that people are very actively following the new missions that are coming up. And so this is from the Solar Orbiter mission, which the data came, there was a press release, I think an hour back, and the images are amazing. So the campfires, so as they call it, I think they are alluding to something called nanoflares. So what happens on the sun is that you get these large explosions, which are many times larger than the Earth. And the cause of this explosion is something to do with magnetic fields. There's a joke in astrophysics that if you don't know why something is happening, magnetic fields are probably doing something. So it's really magnetic fields here. You really see strong magnetic fields at locations where you get these large blasts, and these regions are really hot, much hotter than the average corona itself. So there was a proposal by Eugene Parker, about after whom the Parker Solar Probe is named. He had this proposal that if we can have large flares, we can have small flares, we can have nano flares. And if we have these really small blasts occurring all over the surface of the sun, that could possibly keep the corona hot. So that's how he wanted to resolve, or he attempts to resolve the coronal heating problem. There are multiple models. Now these campfires, as the researchers are calling it, they seem to be alluding to the presence of nanoflares, nanoflare observations. So I would wait and see what the researchers are doing, because there are very established researchers trying to work this out, and I'm really looking forward to what they find with this new data.
Great. Thank you, Vishal. That was a wonderful answer. And thank you for our audience for asking such wonderful questions. So we have another question. So how close can we get to the sun before our craft stop working? And so I believe that this one might be for either Vishal or Téo.
Yeah, I can speak to this a little bit. Exactly how close that distance is, I can't answer specifically, but what I can say is that we currently have two missions whose entire purpose is to go very close to the sun. So we have Solar Orbiter, which is what gave us these campfire images that we've just been discussing. And the plan for Solar Orbiter is to go into a little bit less than a third of the distance between the Sun and the Earth. And it can withstand the temperatures that it experiences at that sort of distance for, I think, maybe five years, maybe a little bit longer before things start to break down a bit. There's also Parker Solar Probe, which is getting closer in, but the preliminary mission time is shorter because they expect that the spacecraft won't be able to stay as close for as long just due to the temperature. And these two spacecraft are the closest ones that we've ever sent to the Sun. So we're really hoping that by getting this closer, we'll be able to learn a lot of stuff that we couldn't learn from even as far away as we are on the Earth.
Great, thank you. All right, so we're running up on our time. I'll go ahead and close with a question for each of you. And this is more about you personally and your experiences. So I wanted to ask each of you guys what led to this summer's work? How did you end up here at FDL? So we'll go ahead and kick it off with Panos, sorry.
So for me, as I'm not like the domain expert on the solar storms, so my curiosity was mostly to apply machine learning and deep learning on actual problems that they have like a massive impact on our civilization and humanity. So FDL specifically, has like this unique position where essentially it bridges, it brings like some of the most important and interesting problems that you can solve. And, I was hoping to be able to use my skills for, on that mission.
Great, thanks, Panos. We're glad you're here. I'll go ahead and turn it over to Bashi.
So for me, I'm like mostly working on the Earth magnetosphere and the relation between Earth and Sun. And like I was like always like we have this large amount of data to process, and I'm doing simulation again. We're producing large amount of data. I was looking forward to use machine learning technique to apply to my research, and like getting like these online courses. They were good, but they would not hit you, with the like actual work you can do. So with FDL, it was perfect because I could practically use those techniques and then apply it for my future research. So, and I learned about this from one of NASA people at Living with Star meetings. So, and then I applied for FDL.
Great, thanks, Bashi. And that's one of the things that FDL hopes to do is to bring in researchers that can then go and bring it back into their field. So we're really excited to have you. I'll go ahead and turn it over to Vishal.
Yeah, I have a couple of reasons actually. It's not just one. The first reason is I just love magnetic fields, and I just love studying about magnetic fields. This is the science part of why I'm doing this. Second is I've been following FDL for the last 3 years or 4 years, I think. So ever since the Heliophysics division came into the picture, a friend of mine attended FDL the first time it was there, and I was really amazed by the kind of work that is being done here, the kind of problems being tackled, the kind of peer group that exists here, and the kind of facilities that you get to solve these or to in the attempt to solve these problems. So that was really motivating for me. And third, I study the sun, and I've been working on the solar wind for quite some time. And I wanted to see if this same can be extrapolated and applied to the benefit of humanity. If I can predict solar storms, that would be great because that will save a lot of money and equipment for various people, and it affects the common man. Tomorrow you're walking and your phone starts bursting to flames, and then there is a model which can say, no, switch off your phone, it's going to burst to flames. I think that's a good enough motivation to work on a project. Yeah.
Awesome. Thank you, Vishal. Thanks for joining us. And we'll go with Tia.
Yeah, so for me, I think it's kind of twofold. One aspect is just being able to learn in a hands-on way is just the best way of picking up all these new skills, both in machine learning and from the physics side of things. There's all these problems you run into, and you have the people around you who can solve those problems and teach you how to think about solving similar problems in the future. And the other side is just being able to work in a team on a problem and see results really quickly, because you're not limited to just what you can output in a day. For example, there's 4 of us and we're all highly focused on one particular question, which means that we can see results really quickly and we can iterate through problems and solve them really quickly. And just that kind of like teamwork aspect is really good.
Great, thank you. And thank you all for taking time to join us today. Thank you to all of our viewers that were able to tune in for this Facebook Live. Really appreciate you guys taking the time. And with that, we will go ahead and sign off. Thank you for joining.
Thanks for having us.
Thank you for having us here.
Thank you so much.